I think at this point, we all know what a JPEG is. It's an image format that compresses images by throwing away information imperceivable to our eyes. But did you know that there's other formats even better than JPEG? WebP, AVIF, and JPEG XL all reduce file sizes by massive amounts, sometimes up to 50%, without compromising on image quality. Imagine how much more efficient the internet could be with file sizes cut down by 50%. Why aren't we using these new image formats then? There's been quite a bit of drama around patents and big tech companies dominating the internet. The outrage reached a fever pitch a few years ago when Google decided to remove experimental JPEG XL support from the Chromium project. I think the reality is a little more complex than online pundits suggest, but regardless of what you think, there's something that gets completely lost in this drama. What did the computer scientists actually do to make these image formats so much more efficient? You can't just magically snap your fingers and make half of the bytes disappear. And why can't we compress images even more than JPEG XL? What is the theoretical limit of image compression? It turns out the answer is less hand-wavy than you might think. In this video, I'm going to describe the algorithms used in image compression, show how these algorithms reduce file sizes in modern image formats, and mathematically justify how to calculate the minimum file size for any given image. Let's get started. The bitmap file format was created by Microsoft in 1987 to standardize how images are stored on Windows computers. Every image is made up of pixels, and each pixel has red, green, and blue values associated with it. Each of the red, green, and blue values is between 0 and 255, meaning that 8 bits are required to store a single value. Bitmap files are uncompressed, so they take up a ton of space. Throughout the video, I'm going to be using this picture of my cat to demonstrate the various compression techniques. The image dimensions are 4032 pixels wide by 3024 pixels tall. In bitmap format, the file size is 36.6 megabytes. The simplest method for compressing data is Huffman coding. If we look at the original image, we can see that most of the pixels are either very bright or very dark. So instead of using 8 bits for each of the possible values, we can use fewer bits for common values like 0 and 255, and more bits for uncommon values like 127 or 128. The variable length code we get is called a Huffman code. I've glossed over a ton of the details here, but I'll leave links in the description to other videos that go into more detail. There is no image format that only uses Huffman coding, so I implemented my own. Using Huffman coding, the cat image shrinks from 36.6 megabytes to 33.8 megabytes. The problem with Huffman coding is that it doesn't take into account the order of the pixels. We could rearrange the pixels in any order and it wouldn't affect the Huffman code. To exploit patterns in the data, we're going to need another algorithm. The LZ77 algorithm uses back references to point to sequences of numbers that we've previously seen in the data. Let's say we use a sliding window of 256 numbers. We see a sequence 11, 14, 11, 15 twice within the sliding window. The start of the second instance is 7 positions away from the start of the first instance. So we can replace the second instance with a pair of numbers offset equals 7 and length equals 4. Since we replace a sequence of 4 numbers with a pair of 2 numbers, we save 2 bytes of data. LZ77 is usually paired with Huffman coding to achieve better compression. This is exactly what the zip format does. We can convert an image into a zip file by right-clicking the image and selecting Compress. Using both LZ77 and Huffman coding, the cat image shrinks from 33.8 megabytes to 15.8 megabytes. The PNG image format was created in 1996 as a replacement for the GIF file format. GIFs were compressed with an algorithm called LZW. However, the LZW algorithm was patented by Unisys, who demanded licensing fees from software that generated GIFs. As you might expect, the GIF format was eventually overtaken by PNG. Let's say we have an image that has a left-to-right gradient. None of the individual RGB values repeat, and there's no repetitive sequences of values. So Huffman and LZ77 don't help us here. PNG fixes this by using various types of filters. For a left-to-right gradient, we can subtract each value from the immediately preceding value to obtain a difference. A gradient with a constant rate of change will have the same differences between adjacent pixels. We can then apply LZ77 and Huffman coding to these values to compress them. This filter is known as the sub-filter. But what happens if we have a top-to-bottom gradient? In this case, we can use the up filter, which is similar to the sub-filter, except that it subtracts the value above each pixel from the current value. You might be asking, how do we know when to apply each of the filters? Each row is encoded using a dynamically selected filter. The PNG encoder uses some heuristics to decide which filters to use for each row, but sometimes it doesn't pick the best one. This is where the effort value comes in. There's a website called squish.app that lets us compare images side by side when deciding which image format to use. The PNG encoder includes an effort slider that controls how thoroughly the encoder searches for the optimal filters. Using an effort value of 5, the cat image shrinks from 15.8 megabytes to 9.4 megabytes. The generalized version of PNG's compression algorithm is known as lossy plus residuals. It also goes by other names, like predictive coding or context modeling. Let's say we have 4 numbers, 970, 990, 1010, and 1030. Overall, we use 14 digits to represent these numbers. But if we look closely, it seems kind of unnecessary to use so many digits when the numbers are so close together. What if we subtracted out the average of the numbers? The average is 1000, so the differences are -30, -10, +10, and +30. Notice how the leftovers, or residuals, are all 2-digit numbers. Now we're only using 12 digits to represent all the numbers. But we can do even better. All of the numbers are collinear, so we can perform linear regression. The y-intercept is 970, the slope is 20, and all the residuals are 0. Using linear regression, we only need 9 digits to represent the data. We can treat any lossy encoding of an image as a prediction about the original image. If we calculate and store the residuals alongside the lossy encoding, we can always recover the original image. If my description of using linear regression sounded familiar, it's because the PNG format already does something very similar. Linear regression can be seen as a variant of the sub-filter. Now we can see an opportunity to improve the PNG format. Instead of applying a small number of filters, row by row, per color channel, we can expand the scope and complexity of the prediction models to improve the compression. The WebP image format was created by Google in 2010 as a replacement for both the JPEG and PNG formats. Although WebP is better known as a lossy format, Google added a lossless mode in 2011. The lossy and lossless modes work differently, so for the time being, let's focus on the lossless mode. One of PNG's major limitations is that it compresses on a row-by-row basis. WebP makes predictions per block instead of per row. Pixels near each other are more correlated than pixels on opposite ends of the image. WebP decorrelates the color channels from each other. The optimal decorrelation settings are determined per block. Finally, WebP includes 14 different predictors, as opposed to PNG's 5 filters. Using an effort value of 8, the cat image shrinks from 9.4 megabytes to 6.9 megabytes. The JPEG XL image format was developed by the Joint Photographic Experts Group, together with Google and Cloudinary. The history of JPEG XL is messy, but let's just go with the Wikipedia date and say it was released in 2021. JPEG XL includes both lossy and lossless modes, but we'll talk about the lossless mode first. The first major improvement is JPEG XL's alternative to Huffman coding. Huffman codes use an integer number of bits per symbol, but theoretically we can use a fractional number of bits per symbol. But how do we use fractional bits per symbol? The original way of accomplishing this was using arithmetic coding. Let's say we want to encode the message A, B, B, B. The symbol A occurs 25% of the time, and the symbol B occurs 75% of the time. Our goal is to encode the message into a single, arbitrary precision floating point number. We start with the range 0 to 1, and divide it up according to the symbol frequencies. As we encode each symbol in the message, we update the range so that we zoom in on a smaller segment of the line. After we've encoded every symbol, we take the shortest length number in the range as the compressed message. Arithmetic coding typically results in a 5 to 10% reduction in file size compared to Huffman coding. The reason Huffman is usually preferred is that the encoding process is faster. And also, arithmetic coding was patented in 1978, and since utility patents are active for 20 years, it was active through the time period when JPEG and PNG were created. In the late 2000s, Jarek Duda invented the concept of asymmetric numeral systems, or ANS. ANS coding is similar to arithmetic coding, except that it uses some tricks to achieve faster encoding speeds. Google filed a patent for ANS coding in 2016. Google eventually abandoned the patent, presumably due to the backlash. Then Microsoft filed a patent for ANS coding in 2019. They were initially rejected, but finally got the patent through after an appeal. These patents probably don't affect the use of ANS coding in JPEG XL, but the fact that they exist is concerning, to say the least. JPEG XL uses a technique called meta-adaptive context modeling, which creates a decision tree to decide which predictor is used for each pixel. One decision tree is used for the entire image. Theoretically, every pixel can have its own path through the decision tree. One of the funny things about JPEG XL is that you can make cool artwork with incredibly small images. For example, this image from the JXL art gallery is only 34 bytes large. Keep in mind that you can only view this image in Safari, since both Google Chrome and Firefox don't support decoding JPEG XL images. Using lossless JPEG XL with an effort value of 4, the cat image shrinks from 6.9 megabytes to 6.3 megabytes. Up to this point, we've only been talking about lossless image compression, but that's only half the story. The vast majority of images on the internet use lossy compression, which dramatically decreases file size versus lossless compression. The idea behind lossy compression algorithms is that we can throw away information imperceivable to our eyes. But how do we know which information to throw away? There's a long list of perceptual similarity metrics we can use to determine whether two images are perceptually similar. The goal is to throw away the information that has the least impact on our chosen similarity metric. For this video, I'm going to be using DSSIM, which is an open source tool developed by Cornel Lisinski. The DSSIM score is between 0 and infinity, where 0 represents a perfect match. Using DSSIM, let's retrace our steps through the history of image compression, this time focusing on lossy image formats. PNG is usually considered a lossless format, but it supports lossy compression through color quantization. The idea of quantization is that we can round the pixel values to a smaller set of values. This smaller set of values appears more often in the quantized image, resulting in a smaller file size after LZSS and Huffman coding. We can reduce the number of possible colors from 16.8 million all the way down to 2. Targeting a DSSIM similarity score of 0.01, the cat image shrinks from 6.3 megabytes to 5.9 megabytes. Even the most sophisticated lossless compression can't compete with the most basic lossy compression. The JPEG image format was created in 1992 to be an extremely efficient way of storing images. The image is first converted from RGB to YCbCr. Human vision is less sensitive to color than to brightness. To take advantage of this, we perform chroma subsampling on the color channels. There are multiple ways of performing chroma subsampling, but the simplest way involves throwing away half of the color values. Next, we separate each channel into 8 pixel by 8 pixel blocks. We then run each block through an algorithm known as the discrete cosine transform, or DCT. The DCT essentially separates out the different frequency components of each block. Since human vision is less sensitive to higher frequencies, we quantize higher frequencies more aggressively than lower frequencies. After we've done all this, we apply run length encoding and Huffman coding to the quantized values. Targeting a DSSIM similarity score of 0.01, the cat image shrinks from 5.9 megabytes to 111 kilobytes. That's a 98% decrease in the file size. We've already encountered WebP lossless before, but now we're going to focus on the lossy mode. After separating out brightness from color, WebP uses different block sizes per channel. JPEG only allows for one set of quantization values for the entire image, but WebP can quantize more aggressively in blocks with few details, and quantize less aggressively in blocks that have lots of details. Finally, the quantized values are compressed using arithmetic coding, which outperforms Huffman coding in compression efficiency. Targeting a DSSIM similarity score of 0.01, The cat image shrinks from 111 kilobytes to 78 kilobytes. The AVIF image format was created in 2019 by the Alliance for Open Media, which is a consortium of software companies. Unlike WebP's predetermined block sizes, AVIF has an extremely flexible blocking strategy, where blocks can range from 128 by 128 down to 4 by 4. It also includes dozens of additional predictors compared to WebP. Instead of using only the discrete cosine transform for each block, AVIF can select from several different transform types, like the asymmetric discrete sine transform, or even no transform at all. Targeting a DSSIM similarity score of 0.01, the cat image shrinks from 78 kilobytes to 29 kilobytes. I should mention that AVIF technically does include a lossless mode. However, the file sizes it produces are so large that even PNG outperforms it in most cases, so I'd recommend staying away from AVIF lossless. We've already encountered JPEG XL lossless before, but now we're going to focus on the lossy mode. Honestly, there isn't much to say about lossy JPEG XL. JPEG XL was developed around the same time as AVIF. Since they were developed independently, their specific implementations are quite different, but they mostly use the same image compression techniques. Targeting a DSSIM similarity score of 0.01, the cat image grows from 29 kilobytes to 78 kilobytes. I was pretty surprised by this result, because JPEG XL is usually considered better than AVIF. It might be that JPEG XL is better than AVIF in the majority of cases, and I happen to use an image that was in the unlucky minority, but who knows? So have we achieved optimal image compression? To answer this question, we need to think about the limitations of our approach so far. Good compression algorithms use the local context around a pixel to select a predictor for its value. Using a larger context and more predictors improves the compression efficiency. Can we take this idea to the extreme? Could we allow for global dependencies and arbitrary predictors for every single pixel? What we need is something like JPEG AI is the first international image coding standard based on an end-to-end learning-based approach. Version 1 of the standard was published in 2025. Despite being an official standard, it's very hard to find any information about JPEG AI. It's barely mentioned anywhere on Wikipedia, and the most popular YouTube video has less than 2,000 views. One of the main use cases for JPEG AI is surveillance. Once you see the list of companies developing JPEG AI, this makes a lot more sense. Unfortunately, the reference implementation of JPEG AI is barely active, the official standard is paywalled, and lossless coding is deliberately excluded to prioritize greater implementation flexibility. It's pretty easy to laugh off JPEG AI as a meme format concocted by Chinese companies to simplify scanning images for Winnie the Pooh memes. That might be true, but when we look at the progression from PNG to WebP to JPEG XL, a fully end-to-end AI algorithm seems like the logical next step. In fact, neural image compression is a highly active field of research, with dozens of papers published every year. Unfortunately, they're mostly proofs of concept at this point, and the results are hard to replicate without very expensive NVIDIA GPUs. However, one paper in particular caught my attention. Deep lossy plus residual coding for lossless and near lossless image compression. Here's the basic idea behind how it works. We can train a neural network where the input is an image, and the desired output is exactly the same image. In the middle of the network, we force all information through a bottleneck. The size of the bottleneck determines the size of the compressed image. After training, we can then split the model at the bottleneck layer to obtain an encoder and a decoder. This is known as a variational autoencoder, or VAE. Check out the links in the description for videos that cover VAEs in more detail. The authors of the DLPR paper claim to achieve a 9.3% file size improvement when compared against JPEG XL lossless. Combining the information from this paper with what we already learned about the history of image compression, there's a lot we can say about the theoretical limit of image compression. First, the compressibility of an image depends on the image itself. Random noise cannot be losslessly compressed. If we generate an image of completely random noise, there's nothing we can do to make the file size smaller without somehow eliminating the noise. And if this random noise comes from a camera sensor and appears in the context of a photograph, lossless compression will have a limited effect on file size. Second, The compressibility of an image depends on the assumed distribution of images in a reference dataset. This makes sense when training an AI encoder, but it's also true for formats like JPEG XL. The prediction models used by JPEG XL are selected to optimize file sizes for images in a benchmark dataset. It's even simpler than this. If you've ever heard the statement, use JPEGs for photos, use PNGs for cartoons, this statement highlights how different formats are optimized for specific types of images. Third, image compressibility is intrinsically linked to encoding time. This is a consequence of the previous 2 points. To optimally compress an image, we need to figure out how the image we're compressing is related to the training data used for the compressor. WebP handles this decision for you at the expense of taking a longer time to encode each image. JPEG XL's encoder takes even longer than WebP because it's even more thorough in its analysis. And it should be pretty clear that neural network-based encoders are even more computationally expensive than JPEG XL. Finally, more sophisticated image compression algorithms tend to directly optimize for file size. PNG locally optimizes each row, and WebP locally optimizes each block, but local optimization doesn't necessarily lead to a globally optimal solution. JPEG XL does look for global patterns in the image, but its context modeling using a binary tree limits the granularity of its predictions. Neural compression theoretically allows for global pattern matching and arbitrarily complex prediction methods. This leads me to believe that current state-of-the-art compression methods will be very hard to beat. I also want to point out another result. It's not a theoretical result about image compression, but it's hard not to notice. Advances in lossless image compression tend to lead to advances in lossy image compression. With neural networks, we can set the objective function to be a weighted average of different objectives. In fact, this is exactly what the Deep Lossy plus residual coding paper does. Their objective function includes a term that controls whether they're optimizing for lossless compression or near lossless compression, which is basically lossy compression with bounded errors. This provides us with a unified framework for reasoning about all types of image compression, regardless of the objective that we want to optimize. If you enjoyed that video, make sure you smash that subscribe button. Check out my Patreon for behind-the-scenes content for every video I publish. I'd really appreciate it, and I'll see you guys next time.